This is the Plato Circuit Formal Lab by Hanan and Pernali. So our experimental goal was to determine the resistivity of Plato in a circuit with a light bulb and a motor fan. So our research question was, what was the effect of Plato on a current and voltage in a circuit that was supplying power to both a fan and light bulb? So some key ideas were that junction and loop rules were used to make sure that no more than 20 milliamperes were being delivered to the bulb, otherwise it would blow out. And we were making sure that at least 300 milliamperes were going to the motor fan to make sure it works properly. And we were able to find that the Plato is an effective resistor because it limited the current flow to the light bulb when connected in series with the light bulb. And a similar current was observed between LED and the Plato. So models. Since the current flow in the path of since current flows in the path of least resistance, the light bulb was placed in series with the Plato resistor, allowing more of the current to go to the fan. And since the current path to LED had more resistivity, we saw less current flow to the bulb and more flow to the fan. And then from the voltage law, the conservation of energy tells us that the total voltage across a circuit should equal that of its power source. And the current law tells us that components in series should have equal currents. And so from those laws, we were able to derive the equation that the change in voltage for Plato plus change in voltage for the LED bulb is equal to the change in voltage for the motor fan. And voltage should be in constant parallel loop, which will ensure that the LED receives 2 to 3 voltages and is not overloaded. So equations that we use was resistance R equals PL divided by A, and the respective variables and what they stand for is written below. And then Ohm's law, which is V equals IR. And to the left right here is a drawing of our circuit.
To bring the circuit diagram to life, we collected the following materials: Play-Doh with a wire kind of running through it, two 1.5 volt batteries with the holders. We used alligator wires and a motor fan, which needs electricity to run, obviously. And then we had the LED light bulb. We connected the battery to the light bulb from the positive side of the battery with the alligator wire, while connecting the Play-Doh to the negative side of the battery. We connected a wire between the Play-Doh and the bulb to make a series circuit, and added the motor fan by connecting a wire from the bulb to the fan, as well as the Play-Doh to the fan. And the Play-Doh again acts as the resistor in this case. We measured and recorded the voltage and current through the Play-Doh, bulb, and the fan using a multimeter. Our potential sources of error in this setup may be that the fact that the multimeter was fluctuating during our readings, so the calibration may have been off, leading to potentially inaccurate readings in the voltage and the current that we were measuring across each of the components in the circuit. Determining the exact surface area is also difficult of the Play-Doh, and letting the Play-Doh harden after a certain period of time, that leads to increased resistivity as the Play-Doh hardens and electrons aren't able to flow as quickly through and as much through the Play-Doh as they would if it wasn't as hard. The data and collections section here shows that our Play-Doh had the lowest voltage across, with the fan showing the highest voltage. The current was the same for the Play-Doh and the bulb, with the fan slightly higher at 1.15. And the resistance was the lowest in the Play-Doh. Resistivity was measured using V divided by voltage divided by current, which gave us the resistivity for both the fan and the light bulb as well as the Play-Doh. The resistivity for the Play-Doh was calculated by resistance equals P multiplied by L divided by A, or P equals RA divided by L. As running the calculations, we see that the final resistivity value for Play-Doh comes out to be about 0.02 ohms per centimeter. Ultimately, the bulb and the Play-Doh resistor had the same current flowing across when connected in series, and the bulb appeared to have very dim light. This may have been due to the fact that we were using 1.5 volt batteries, where the bulb needs 2 to 3 volts to run effectively. As shown in the pre-lab, a future study could investigate varying shapes or sizes of the Play-Doh and their effect on the resistivity of the Play-Doh. Once power was distributed more heavily to the fan seemed to achieve optimal speed and function properly. And as mentioned in our sources of error, the multimeter was off in its readings and may invalidate some of our data.